So, different devices use different types of analog to digital converters. Um, so, the major thing when we're looking at these different converters is they all have different trade-offs. So, there's no like perfect converter, but I'd say for the most part these are all good options. It just depends on the situation which one would be the best option. So, the first type is a successor of analog digital control converter that we're going to talk about is a successive approximation converter. Um, so the basics of this is that the device has something called a comparator, which basically determines whether or not a signal is basically above or below your input signal. All right. Using that information, it tells a controller basically to adjust the digital value. All right. So it'll adjust it from being either maybe 000 to 1010, and that would then affect the signal that goes into a digital to analog converter, which sends another output signal to the comparator. So basically, it continuously adjusts this E star value until it equals EI. Right? So this takes some time, and it depends how fast um, the clock or how fast the digital analog converter can convert these numbers back and forth. So typically, most analog to digital converter, successive approximation converters, typically have value registers between 12 and 24 bits. They can have clocks that run at 100 kilohertz to megahertz. All right. So there are some errors that are due to the digital analog conversion and the comparator, um, uh, but overall they're pretty strong uh, uh, in terms of their speed. So typically, I would say the speed is proportional to the number of bits divided by the clock frequency. So the more bits you have, and the the longer time it takes, and the faster you go, the less time it takes. So those are the ways you can improve the measurement speed for the successive approximation converter. Okay. Um, the second type of converter is the ramp integrating converter, um, and basically it is typically used for very low voltage measurement signals. Um, so the nice thing about it is it typically, even though it's a slow process, but typically because of the way that the system works, is it eliminates noise. So it's a very way to get good accurate measurements. But the time you can see is related to there's a clock, just like we did for the successive approximation converter, again, but the time is related to the number of bits to the power of 2. So you can see that that's going to take that's going to be a much larger number than the time it took for the successive approximation converter. Okay, so again, you don't have to worry too much about the physics of how exactly it works, but the major thing is that it can be used to determine very accurately, it has very high accuracy. It's good for low voltage signals, but it's going to be pretty slow most of the time. Um, and then the last type of converter is the fastest converter. It's a parallel converter. Um, Basically, it uses a voltage divider and a series of comparators um, uh, in order to take your measurements. It's great if you have really high frequency measurements, go to 150 megahertz. Um, but the issue is that depending on the number of bits you need, you have to have a certain number of comparators. So, for example, if you want just an 8-bit uh, analog digital converter, you need 255 comparators. Okay, so in conclusion, what I want to kind of highlight here is that is probably the successive approximation converter is probably the most common. It's pretty fast. There is some issues with accuracy due to the sample and holds due to the digital analog converter and the comparator having some errors with it associated with them. But overall, it's usually a pretty solid system, pretty good speed, and relatively low cost because it only has a single comparator. The ramp integrating converter is a very good tool for measuring static signals where frequency is not super important. and it can be used to measure typically very low voltage signals very accurately. Uh, while the parallel converter is a great option, the issue with it is its cost. It's very expensive due to the amount of hardware required to have it to work. So for higher bit converters, you have to have a lot more comparators, and that causes the chip to be much more expensive. Um, so just keep in mind when you're looking at different data acquisition systems, they typically will have one of these types of converters within them, and this will affect the performance of the digital acquisition device.